associated with it. But again, it's basically loam, meaning that loam has clay, silt, and sand all present in the sample, but silt tends to predominate. Basically, it's a loamy soil, but silt is the dominant texture of the soil. Now, immediately when I pour this into my hands, I can feel the very flowery, smooth, fluffy nature of this material here. And that's what a silt loam is about. It's the abundance of silt has this very smooth, flowery, flower-like feel associated with it. It's important that you have the appropriate water content to the soil. The ideal moisture content when you're texturing the soil would be like if you had, see, I added a little too much water there, so I need to put a little more soil in it. The ideal moisture content would be like you would observe if you went out after a rain and the excess water had drained out and the soil was what we call field capacity. It was holding all the water it can against the pull of gravity here. So now I'm texturing this silt loam soil, and I'm mentally, remember what I'm doing, I'm mentally in my mind thinking now, okay, how does a silt loam sample feel? I know that this is a silt loam, and so then I practice here, and I'm training my fingers to recognize. Now, I definitely can feel more stickiness associated with it, because this also has a fair amount of clay associated with it too. So, but this would be a silt loam sample here, and it's smooth and certainly has much more body, not much more, but it tends to even be a little more bonding together than the straight loam. Okay, let's do the sandy clay loam texture next. Now, this will basically have a loam feel, but it'll have sand and clay associated with it. So it's basically a loamy soil, but it has sand and clay. So now let's see how this feels. I washed my hands in between here, so I don't have any of that silt loam material on that we textured just the previous sample. So wetting this sandy clay loam up. Now with the clay, I should be able to have some ribbon associated with it, and that would be because of the clay content of the soil, and I should also feel the sand content in there as well, because there's a good proportion of sand associated with it. You'll notice that it takes me a little while when you have a dry sample, and in an FFA soil judging contest we will give you some, since texture is so important, we will give you some unknown texture samples just simply to texture, to evaluate you as far as your texturing skill is concerned. So you'll need to use the water bottles that will be provided, and it'll be up to you to take the dry samples and get them at the proper moisture content here. And sometimes you have to, sort of like kneading dough, you need to knead it quite for a few minutes and somewhat rigorously so that you can get the water manipulated in. Okay, now again, I feel lots of stickiness, and when I rub it, I can feel a good bit of clay of sand associated with it too. The stickiness, of course, has to do with the clay, and the sand has to do with the sandiness, and that all comes out then to make this sample a sandy clay loam. So let me place that here, and you can see it's again, they're starting to ribbon more as we increase our clay content. Now the clay loam sample will have less sand content, and the clay will be the predominant soil separate associated with it. So now as I moisten and wet this clay loam sample, I should again have a ribbon that won't look much different from the one that I just dealt with. Neither will the stickiness feel a lot different. The big difference will be that I won't be able to feel the sand content, as much sand. And it will have definitely silt associated with it, and a fair amount of silt, but not enough to call it. There is a silty clay loam texture, and if you order these texture samples from the Soils Club, we would provide you with anywhere from 10 to 12 samples that would give you samples of some of the textures that I'm not demonstrating. Silty soils are not very common in Arizona. They are in the midwestern part of the United States, but not in Arizona, so we're not quite so concerned about silt loam and silty clay loam type textured soils, because we simply don't have many of these soils. If they are present, they're generally found over in the Yuma area along the Colorado River. Okay, so now I've got, again, boy, this is so sticky it hardly even wants to ribbon. It's hard for me to get it at the right moisture content, but it's certainly sticky and it ribbons to some degree here. So I'll place this now, and it again makes a ribbon somewhat similar to the sandy clay loam, but it has a lot of an expanding type clay in it, and it's just so sticky. You can see how it's adhering to my fingers here. It's just really difficult to get a good sample. The last textural class that we're going to deal with is the clay, and the clay textural class would be, of course, very sticky, and it should make a very prominent ribbon. I need to pause temporarily because my hand is so full of and sticky with the last sample. I need to wash my hand one more time before we texture the clay sample. Remember, that's always a good idea to clean your hands off between the times that you texture different samples so that you can really get a good evaluation of the characteristics of the sample that you're working with. Okay, now we're doing the clay textured sample, and this will feel very sticky because it's clay. You see, it doesn't describe any other constituents in the soil. It just says clay, so that means the clay totally dominates this soil. So it will feel very sticky, and it should really make a prominent ribbon as I squeeze it between my thumb and forefingers. And clay is difficult material to wet up. Sometimes you have to work at it quite a while to get it to absorb the water. One of the things that you'll notice is that when you're texturing clay soils, that they'll really soak up the water. Look at how this is behaving now. You see what I mean now by a good ribbon? The other thing on a close-up will show you, look at the shine on this clay sample. You can see how it shines because of the high clay content of this soil. My goodness, does it really adhere together. And as I squeeze it between my thumb and forefingers, you can see how prominently the ribbon forms for this particular soil. And this is what we would call a very good ribbon. So you can see how it very stuck together very well. Now let's run back over these samples again, and starting here with the sand. Remember, the sand had a very gritty feel and it didn't adhere and hold together well at all. The loamy sand had a little bit of tendency to hold together, but you notice it breaks apart very readily. The sandy clay loam, you see when I touch it, it doesn't fall apart. It adheres together. It's still loamy and it has an abundance of sand, but a sandy loam is a good texture for irrigated agriculture because if you can add the water, it's easier to manage as far as keeping track of the tillage practices here. This is the loam, and when we felt the loam texture, a loam feels like it has about equal proportions of sand, silt, and clay. This was the silt loam, felt very smooth. It will make somewhat of a ribbon. It doesn't show it too well here. But then when you get to these three textures with clay in their textural class name, the sandy clay loam, the clay loam, and then the straight clay, you can see that you get very prominent ribbons associated with them, particularly the clay, and moderate type ribbons with the sandy clay loam and the clay loam here. Let me just feel this clay loam sample again. It will make a nice ribbon if you work with it some, but it's a little bit difficult for me to at this time to get it to demonstrate it too well. So there are the textural classes in, and how you go about determining what textural class the soil falls in. So after you've estimated, after you've felt the samples and dealt with the sand and clay content, then you go, of course, you fit it into one of the 12 classes on the texture triangle. We just finished talking about the clay. I did not demonstrate a sandy clay. We did have a sandy clay loam and a clay loam, and we had a loam, we had a sandy loam, a loamy sand, and a sand. We had a silt loam sample. Did not demonstrate a silty clay, or like I mentioned, the silty soils are not real common. Now, when you're judging the soils on the FFA soils contest, the actual scorecard that you'll use does not have those textural names on them. You'll see terms like coarse, medium, fine, or moderately coarse and moderately fine. And so you actually aren't going to make note of the textural class. You're actually going to make note of placing it in one of those categories. And all that's been done is that the texture triangle has been, instead of grouping it and asking you to place it into one of the 12 texture classes, we've simply grouped some of the textural classes together, and I've colored what's called the fine textural classes, the sandy clay, the clay, and the silty clay, where clay is the dominant. And notice I've colored it red. I did that intentionally because to indicate the major problems associated with a clayey soil in terms of their management. Across the middle part of the triangle, colored yellow, are what we call the moderately fine textured soils: a sandy clay loam, and a silty clay loam. Those are classified as moderately fine textured soil. So when you're texturing the soil, you would make a decision on the appropriate texture class, but then we do some grouping once you decide that. The medium textured soils are the loam textures, the silt loam, and then a silt texture. The sandy loam is colored blue here, and that would be what's called a moderately coarse textured soil. And then a loamy sand and a sand would be considered coarse textured soils. So actually on the texture, on what you do in your judging, is that you will end up grouping the soils based on into one of these 5 categories rather than using the 12 textural classes. But you should be learning about the 12 textural classes, and then if you know those well, that means you also know the groupings by grouping them into one of the 5 categories. I started with this sample, and to begin with, and I mentioned about sieving it into the fine earth fraction, which was smaller than 2 millimeters, but there's also particles in the soil that are larger than 2 millimeters. We call them coarse fragments. So you do need to estimate the percent coarse fragments in the soil, in the surface horizon on the soil judging scorecard. And we have 3 categories that relate to that: less than 15% coarse fragments in a soil horizon, 15 to 35%, or greater than 35% coarse fragments. And that's simply an estimation that you make as you evaluate the soil. And so these would be the categories that I just mentioned, and these schematics here illustrate this. The blackness in this circle here represents 10% of the volume occupied by, well, coarse fragments, if you're talking about coarse fragments, or 20% here or 30% here. And so this is simply an estimation that you need to make. Many of our Arizona soils do not have coarse fragments, particularly the irrigated soils, in them in any large quantities. But it's something that we must be conscious of and we don't want to ignore. So percent coarse fragments in the soil is also part of the particle size classification of a soil. And so you need to be aware of that, and that's also therefore one of the factors on the soil judging scorecard. Well, we've talked about the individual particles in the soil. Most of the time these particles are aggregated together or grouped together to form aggregates. So let's move on to the next characteristic of the soil. It's structure, soil structure. So now we're going to talk about soil structure. The terms on the scorecard to identify the soil structure are granular or crumb, block, massive, prismatic or columnar, platy, or single grain. These are the terms that are used to describe structure. And here I have some examples of the structure types that were just identified for you. If the particles are aggregated together into grains or granules, then of course we use the term granular structure. So this would be granular. Sometimes the particles are grouped together into basically a blocky type structure. And sometimes the blocks have sharp angles associated with them, like expressed here and on the edges, and sometimes the angles are quite rounded. But basically they're a blocky structure where the vertical dimension is essentially the same dimension as the horizontal dimension. That's not true with the prismatic or columnar structure, and this would be an example of a prismatic structure. And of course prismatic means, and the difference between prismatic and columnar has to do with the top of the prism. If it's rounded, it is called columnar. If it's more flat like this it's called prismatic. So here it's the vertical direction of the dimension is much greater than the horizontal dimension here. And so this is called a prismatic type structure. There are two structureless situations. One is where you have a mass of soil that we call massive, and that's what I'm holding, is a mass of soil in my hand. And this is a massive situation, or no structure. And you can have a situation in the soil where you have nothing but single grain or individual grains. Usually that's very sandy type soil. And so it's simply individual particles here. Now I have a schematic picture that illustrates the same thing, that shows these. This would represent the granular type structure, and this would represent the single grain type structure here. They look somewhat the same here, but these are many soil particles aggregated together into a grain shaped size. These are individual sand particles here, and this is to represent drops of water, because structure very much impacts and affects the rate water moves through a soil. So we factor that in as we make decisions about the ability of a soil to take water in and transmit water. This would be, of course, the prismatic structure and the blocky structure, which both of them have intermediate type rates of water movement through them. This is representing a massive structure, which is water tends to move quite slowly through, whether you have a massive type condition. And there is a type called platy structure that I did not have a sample to illustrate to you, but this would illustrate the platy structure. Okay, so that's how it looks like in a schematic here. Behind me I have some monoliths, some profiles of different types of soil. Let me see if I can point out some different structure types here. If cameraman can zero in on this, would be a blocky. You see this horizon goes from about here to here, but this basically has a blocky type shape associated with it. So that would be blocky structure. And then if you go below this blocky structure, it's almost a mass. And so you have a massive type condition. That would certainly be true here. These are broken chunks here that fell out of this particular monolith. But you see how everything from here to here is simply a mass of soil. And so we describe that as a massive type condition. And below that, although it doesn't show very well, is what we call single grain. In other words, this soil has no structure. It has a massive condition up in the upper surface horizons, and in its subsurface horizons, it's a single grain. You have coarse gravel particles like I'm pointing at here, or nothing but sand here. And so if I could hold this in my hand, it would be a single grain type condition here. Okay, this soil has a very well-defined blocky structure. Look how prominent these blocks are. Now some of that, it sort of broke out this way a little bit with handling and drying. But still, this is a very excellent blocky structure here. And so this would represent a blocky type condition here. This is quite a clay soil. It has a coarse fragment on the surface. It too has angular. Sometimes we talk about them being rounded, which is subangular blocky. Sometimes they're angular blocky. You don't have to distinguish between the two, but this has sharper angles, these two, and some of these blocks, especially in the first soil, did not have that. Moving over to these two soils on the far right, they're more granular in nature, although the granules are so small, probably you can't get a good idea. This dark colored soil comes from the White Mountains area of Arizona, and this also comes from higher elevation, and it has some granules associated with it, but it's also quite sandy natured here. So it's not quite as easy to see structure when you're talking about it in the soil itself. So it doesn't show up quite as prominently as these distinct PEDs or aggregates that I've been showing you here as specimens here. So the specimens make it easy to identify. It's not quite so easy when you actually get out in the soil. Okay, the next characteristic of the soil, I'm going to push that aside, is what we call the consistence of the soil. And the consistence of the soil, these are the terms that are used to identify soil consistence: loose or very friable, friable, firm, or very firm. So then what is consistence? And well, consistence has to do with the ability of one to manipulate or spade or cultivate the soil, or how easily it's tilled. And that's very much a function of the water content of the soil. And so I have some aggregates here that are moist that I'm taking out of the plastic bag, and I have some aggregates that are dry from the same soil. And the consistence of a soil is determined as follows. You take an aggregate from the soil, you hold it between your thumb and your forefingers, like so, and then you apply pressure, and you make a mental note of how much energy it takes for me to break or rupture that aggregate. And so I can try it a couple of times here, and I make a mental note. It sort of takes a gentle pressure to break this particular sample. If I try it when it's dry, I can hardly break it, because the dryness really makes the soil very, very difficult to break. And that's, of course, why you don't cultivate or plow the soil when it's real dry, because the soil adheres and sticks together so much. So then the decision that I would make back to the scorecard over here is that I would identify it took a gentle pressure. Loose means that the particles don't adhere together at all, so you can't determine the consistency of the soil. Very friable means that it takes very gentle pressure. Now the sample that I just characterized took a gentle to maybe a moderate type pressure, and we use the term friable, so I would call that a friable soil. Firm means that it takes a moderate type pressure. You know, you can still break it, but not too handily. And very firm means that you can hardly break it between your thumb and your forefingers here. And again, the consistency of the soil is very much related to the clay content or the texture of the soil, but they are independent characteristics that we do determine. Now, organic matter content of the soil we're always, the more organic matter we have in the soil, the more productive the soil is. So we need to make an estimation of the organic matter content of the soil. And if it's less than 1%, we would obviously check that. And if it's from 1 to 3% or greater than 3%, those are the categories on the soil judging scorecard. Now there's only one way to determine the organic matter content of the soil, and that's in the laboratory. You must do an analysis. Well, if you're judging the soil, how do you do it if you don't have an analysis here? Well, you have to just simply estimate the organic matter content, and that's primarily a function of the color of the soil. So let me get some samples here that demonstrates different colors, and we'll relate that to the organic matter content. The texture samples that you might purchase from the Soils Club would also provide you with the organic matter content of those samples, so you could also use those in your training process to help you with estimating the organic content of the soil. So let me go get my samples now to demonstrate and help you with the evaluation of organic matter. Okay, if you want to know the organic matter content of the soil very accurately, as I mentioned, you need to test it in the laboratory and get the actual organic matter percentage. However, soil scientists do have books of what we call Munsell soil color charts, and you won't need to deal with those, but they have little chips of different colors in them in the books, and then you can match up, and we utilize this information too, or not this information, but this technique for evaluating the color of the soil, so that we can, when I describe a soil as a certain color, I can relate it to a certain chip, I being a soil scientist, and then someone else would know exactly what colored soil I was talking about. There's really three constituents of the soil that determine its color. It's organic matter content, it's iron content, and then the presence of minerals in the soil. And let's take a close-up here at 3 different types of material that demonstrates this. This black soil on the right is, of course, high in organic matter. That's the soil that came from the White Mountains area. And this has about 6 or 7% organic matter. This sample in the middle, of course, is very red, and it has an abundance of iron. So a black soil is black because it's high in organic matter. A red or brown soil are those colors because it's high in iron. In Arizona, we also have oftentimes soils, the minerals in the soil, and particularly caliche, as you see in this particular sample here, will also color the soil significantly here. And of course it will turn it white, but we're not going to be estimating the caliche content or calcium carbonate content of the soil. We're going to be determining the organic matter content. Let me go back to my texture samples that we had earlier. Remember, we talked about these are the same texture samples as we dealt with before. And let me just tell you the approximate percent organic matter in these samples here. These 3 samples, the first 3 samples, the sand, the loamy sand, the sandy loam, happen to be less than 1% in organic matter. This probably is about 0.7 or 0.8%. This loamy sample, you can see how it darkens up. This loamy sample falls in the 1 to 3% range. It probably has about 1.5% organic matter. The same thing would be true of this sample here. It's probably got about 1.5% sample. This purplish soil, the clay texture, and then this brownish soil, this definitely would have less than 1%. But the purple soil is real difficult to evaluate because the purple color, the uniqueness of this soil is it's such a specialized soil, different soil, that it's a hard one to estimate here. I also want to point out that this clay loam sample, I mean, it makes a big difference. Look at the sample dry and look at the sample moist. So remember that the moisture content of the soil, you see how it darkens up when you add water to the soil? So you got to be careful that if you look at it dry, it doesn't look like there's much organic matter, and yet when you add water to it, it darkens up. And this sample probably has about 1.5, maybe even as much as 2% organic matter. Again, let's look at the monoliths behind me, and we'll relate to the organic matter content in these. It may not show up, you know, I don't know how well this is going to show up, but this first soil over here probably has less than 1% organic matter. Not probably, but does. Probably got something like 0.7 or 0.8%. This sample comes from the Maricopa Agricultural Center. But there are soils in the Maricopa Agricultural Center that do run slightly over 1% and as much as 2%. So it depends on where you sample on the farm. This has in the 1 to 3% range. You can see both of these darken up, and they would be in the 1 to 3% range. This is much closer to 1. This probably has about 2%. Now, I'm only talking about the horizon I'm pointing at. If you look lower in the soil profile, of course, the organic matter content is considerably different. Notice the red color of this soil. So this has an abundance of iron, has a high iron content. And this soil came from the Madera Fan area as you go down to in the Green Valley area, Madera Canyon area. And so it's much higher in iron content. And so it's redder in color, obviously. This is that purplish soil I was talking about, and it's a clay soil derived from shaly material, gray, purplish shale, and that's why it looks like it does. These two soils, this soil would be greater than 3%. This soil is right at 3% organic matter. And so this would be, again, without knowing an exact analysis, why I can't, tell you without doing a lab analysis, I can't tell you. In a contest, if it's a marginal sample, we would of course give credit for both, because we don't know ourselves unless we do the actual analysis. Okay, so now we've done the particle size distribution, textural characteristics of the soil, we've done the structure, we've done the consistency of the soil, we've evaluated the organic matter content, and so we've really collected quite a lot of information about the soil. So what else do we still need to do to make an evaluation or judgment about the potential of a soil? Well, we've been working on the soil, individual soil properties, and the left side of the soil judging scorecard, we've determined the texture of the soil. We estimated the amount of coarse fragments, talked about that as being an important factor. We determined the soil consistence. We determined the soil structure. We determined the organic matter content of the soil. And remember, these are all determined on the surface AP, or surface horizon, that we cultivate. Now we need to talk about the available water holding capacity of the soil, the water intake rate, and other factors that are listed on the that have to do with the soil profile. Now, the available water holding capacity of the soil, and now we're still talking about the surface foot. We talk about it having a high water holding capacity if it holds more than 1.5 inches per foot of soil. If it's from 1 to 1.5 inch, it's considered a moderately high or moderate. And anyway, these are the categories that we use to evaluate the ability of the soil to hold water once it's applied as irrigation water. Now, the single most important characteristic that determines this is the textural characteristic of the soil. And now you can understand why I spent so much time on the textural characteristics of the soil. So the texture triangle, and I'm using the color triangle here that had to do with the, grouped it into the coarse, moderately coarse, and so forth categories here. If we talked about a soil having a high water holding capacity, really all of the clayey soils, the moderately fine textured soils, and the loamy soils, really in Arizona, all have high water holding capacities. The sandy loams have the 1 to 1.5 inches, and then the loamy sands would be the lower categories, less than 1 inch per foot of soil here. So to make the decision about, wrong card, right? To make the decision about the available water holding capacity of the soil, we primarily relate to the textural properties of the soil and make the decision based on texture, and that's why we spend so much time on texture. The same thing can be true of the next decision that we make, that has to do with the ability of the soil to absorb water, the water intake rate of the soil. Clearly, the sandy loam and loamy sand textures would have a very rapid intake rate. The moderate textures would be the medium textured soils, and perhaps, well, certainly all the medium textured soils, and maybe some of the heavier textured sandy loams that are approaching loamy soils. And the slow would be, of course, the fine textured soils, the clays, the silty clays, and sandy clays. So again, we make this decision based on the textural characteristics of the soil. So knowing about the texture characteristics of the soil is extremely important, and that's why we devoted so much time to it, and you should spend a lot of time developing your skills as far as texturing is concerned. Permeability of the soil. Now we move to the right side of the scorecard, and that deals with the characteristics of the profile. Permeability of the soil, you'll notice, uses the same terms as the water intake rate, but now we're going to zero in on the horizon that most restricts the movement of water after it gets into the soil. And later on this tape, we actually will be judging a soil at the Maricopa Agricultural Center, so I'll explain more in the field as we deal with this later. But the permeability of the soil refers to the ease that water, air, and roots can move through the soil. So that's the permeability of the soil. The effective depth, the depth of the soil, has to do with how deep the roots can penetrate into the soil. And we talk about a soil as being a deep soil if it's greater than 40 inches to anything that limits the root penetration. Moderately deep would be 30 to 40 inches, shallow would be 20 to 30, and very shallow would be less than 20. This next little schematic illustrates that. So this shows if a soil only has 20 inches of soil before it hits something like bedrock or very coarse gravels and sands that would limit root growth. Well, obviously the effective root penetration would be limited by that. Shallow soil would be if it's from 30 to 20 inches, and 30 to 40 would be moderately deep, and if it's greater than 40 inches, we talk about it as being a deep soil. So these are very important parameters as well of the profile that need to be identified and will relate to the soil. We have a few more characteristics about the soil profile to talk about, and then we'll collectively consider everything together and make a decision about the land capability of that land for growing cultivated crops. We need to talk about the available water holding capacity not only of the surface horizon that we dealt with earlier, but we also need to talk about the water holding capacity of the soil profile. And again, we use the terms high, medium, low, and very low. And again, that's a function of the textural characteristics of the soil and the depths of the different horizons that exist in the soil. So again, that's primarily relates back to the textural properties of the soil and the thickness of the horizons. So that would be an important characteristic that we should deal with when we're concerned about irrigating the soil and how frequently we have to irrigate it. There are two chemical properties that are important: the salt content of the soil, number one, and this would be data that would be provided to you at the site. This is laboratory data. There's no way that this analysis can be even estimated in the field very accurately, because it's strictly a chemical analysis. And so the units that are used are millimoles per centimeter, conductivity term, and you'll have to study a little bit more about that. But if it's less than 4 millimoles per centimeter, and this is an electrical conductivity term, millimoles, and centimeter means that the little electrical plates that where you test this are 1 centimeter square and 1 centimeter apart. This is a standard routine way of measuring it. A slight would be hazard problem would be a test of 4 to 8 millimoles, and if the test was 8 to 16 or if it was greater than 16, this would be provided to you at the site and would be, this is a gimme as far as points are concerned. You should never miss these 2 points, but if they are if the soil does have a high salt content, you need to take that into account as far as its potential for crop production purposes. The same statements could be made about sodium. The sodium content of the soil is measured by determining the percentage of the cations that are satisfying the negative exchange sites in the soil, and how many are sodium is very important. If they're less than 7%, we consider that a none, and slight, 7 to 15, and 15 to 30, and greater than 30. Again, this would be given at the site on the card that identifies the site for you. Now, all of that information then will be used to collectively make a decision about the capability of that land, soil, for growing cultivated crops under furrow type irrigation. And we call that the land capability classification. So we're going to, the land capability classification is a system used extensively by the Soil Conservation Service to identify how good the land is for growing crops, irrigated crops in this case. Class 1 would be no problems, excellent land. Class 2 would be land that has some sort of a moderate problem. Class 3 has a severe. Class 4, very severe. And actually classes 5 through 8 really are not even suitable for growing cultivated crops. So we need to make a decision about the land capability class for, it's an interpretation about the made to grow crops under furrow type irrigation in Arizona. And so we have the class 1 through 4 and 5 through 8, which are not suitable for cultivated land here. Now, all of the things we've talked about so far are kind of in a table form. I know this is too much information to deal with at this point, but this would be available to you, and you need to take and consider all of that information together and make a decision about the suitability of the land for growing cultivated crops and under furrow type irrigation. Well, the final part of this tape is hey, let's go to the field and let's judge a soil in the field. So we're going to travel to the Maricopa Agricultural Center, and we're going to judge a soil on the farm, and it'll reinforce some of the things that I've said in this early part of the tape that have to do with determining the properties of the soil and then making ultimately the decisions on what that soil is suitable for. So let's head to Maricopa now, and I'll see you there shortly.